Okay, so we've come to the end of our second masterclass where we've looked about concurrency. We've looked at concurrency, and we're now going to have a short discussion around concurrency. And so, Joe, I mean, what's unique about the Erlang style concurrency as it's been coined?
I think it's probably the first language that really implemented an agent model. I mean, it consists of lots of small processes with no shared memory that communicate through message passing. So it's an object model with messaging, but it's a proper object model with messaging. And that essentially decouples the sender from the receiver, and there's no shared memory, so kind of things with mutexes and releasing mutexes and things like that go away. And it also behaves the same on all different operating systems, because it's not using the concurrency model of the underlying operating system. And that makes it very powerful.
So what you see are the major advantages towards concurrency models in languages which have shared memory?
I think it allows you to build systems out of small communicating components. So if you don't get that isolation between the components, the systems tend to become very, very big. And they kind of are very tightly coupled. But the way you design things in Erlang should be from a lot of small, loosely coupled components with well-defined protocols in between them. And that makes it easy to reason about them and easy to debug them. Because, I mean, from the point where you've got a message into a process to where you get it out, it's purely functional. Or you can write it in that way.
Sure.
And if you're careful, you can write most of the system without any side effects, apart from this message passing side effect that you get at the boundary of a process. That makes it very easy to reason about it.
I mean, certainly our students find Java threading very complicated.
Oh, it's
they start to write GUIs, and it's their mental picture of what's going on when they do a Java program is very hazy.
Yeah.
I think. Whereas I think with Erlang, it's a very clear mental model of these separate processes.
Right, and I think
modeling the world.
Principle of observational equivalence. Two systems are equivalent if they're observationally equivalent. Is a very strong principle. So it's as if you've got this black box, you send a message in, and you observe a message out, and it's the wrong message. You know it's something that's wrong inside.
When did links come into picture and the whole concept of error handling? As I've not seen it in any other programming language.
It came in very early. Well, very early. I say we experimented with lots of different versions.
Was it Mike who came up with the idea?
Mike came up with the idea of links, yes, and it was actually it was to solve a different problem. That was the problem of zombie processes when things go wrong. Because if you have lots of processes who are coordinating a computation and one of them fails, quite often it's meaningless to continue. So in fact, there are two mechanisms, links and monitors, and they're actually used for different purposes. Yes. Links should be used to collapse whole collections of processes that are collaborating. Monitors should be used for an asymmetric. I mean, if you've got a server with thousands of clients, you don't want to crash. Let me see. If one of the clients crashed, you don't want to crash the server because it would affect all the clients. But if the server crashes, of course, all the clients you do want to crash. It's very asymmetric. But if you've got 3 or 4 processes linked together without a client, in a peer-to-peer system, then you may want to crash that little graph of processes. So you can set these up independently.
And that's very nicely designed, I think, that the way that fits in with communication and so on, and the way you can halt that. It's interesting if you look at, I know the people who did work on extending Occam with dynamic process spawn and so on, found that very difficult. I mean, they found, they had a notion of poison, but it was rather ad hoc, and it was clearly not, it was bolted on to a language.
And it was very important for me to try and make it work the same way in a distributed system as in a uniprocessor system. Just because I want to debug it and test it on one system, I want it to behave in the same way. I hate these things where you've got to program it one way if it's on one processor, and a completely different way if it's distributed. I want to program it the same way on both.
It took me a while to actually realize the importance of the asynchronous propagation channels for error messages. Because what's running on one node, as it's asynchronous communication, can easily be distributed in a cluster of nodes, and you can actually use the same mechanisms in your distribution as you're doing locally.
Yeah.
The only delta is you've got a network in between.
Before I did this work, I used to be a physicist, and so these computer scientists who say you can do synchronous communication, you're breaking laws of physics. You can't. It's rays of light, and there is differential information in the system.
I guess there are some disadvantages of asynchronous communication in Erlang. I mean, you can have mailboxes that grow,
you have to be aware of that.
And I guess that raises a general question, which seems to be.
But synchronous things, you will break the laws of physics to do it. So you can't.
Breaking laws of physics that's a good challenge.
That's no.
So Simon, before you started teaching Erlang here at the university, what were you using to teach concurrency to the students?
Well, Kent has a long history of working with Occam. So we were teaching Occam and we were teaching Occam Pi, which is a dynamic version of Occam. So we were teaching something similar. We were teaching separate processes. But of course Occam has a different model in that there are channels, explicit channels, and there are certainly advantages in that, where you can look at an Occam program and you can see, here's a process, here's a channel. Whereas in Erlang, it's rather more implicit.
Because we were playing
structure.
with the transputer when we developed Erlang, so
but
certainly aware of Occam.
Yes, but
like
I guess
the folding editor.
Well, I think that was one of the things that put a lot of people off.
Oh, that was a great thing.
But some liked it and some didn't. But I think one of the problems there was it didn't really get traction, and it's also got this imperative model in each process, which is slightly
it also had some weird fairness. I mean, the transputer had some funny things about fairness, because if you had what in Erlang terms would be a receive statement with multiple branches, the one at the bottom quite often wasn't fairly scheduled. And if they were all equal. But,
and I think, I suppose also the problem there was tying a language to an implementation. That you can run Occam not on the transputer, and you can run other languages on the transputer, but they were very tightly coupled.
Yeah.
So I think
possibly too early as well.
I think our students like. I mean, we talk. So we've been teaching message passing concurrency here for 25 years. So in that sense,
I think it's one of the foundations of computer science.
Yeah. But lots of places don't.
Yeah.
But I suppose
that's worrying.
What's nice about Erlang is that we can teach functional programming and communicating process-based concurrency in one language. And that's a win.
So you teach shared memory processing as well?
Well, we teach it, they learn Java.
Oh dear. Oh.
I have another question here now. The whole embedded space has always been a very sequential affair. How do you see, well, looking at C, using C to implement
not our embedded.
No.
The Ericsson embedded stuff has been highly concurrent.
But where does the Erlang come in and fit into the whole embedded space?
It fits in very nicely, actually. I mean, Erlang is actually quite an old language, so it's developed it started in about 1985, and the first implementations were running on machines with well under a megabyte of memory. So I mean, the virtual machine.
So you can take the virtual machine.
Yeah, I mean, the virtual machine is quite tiny now. It's become slightly more bloated with time, but you can get a good Erlang system in 5 megabytes quite easily. And so at Ericsson we're running it on ARM9 processors and doing embedded applications.
Oh, interesting.
And,
I mean, there is Erlang running on Raspberry Pis, there's Erlang running on the Parallella board, on Beagle boards.
Yeah.
So
we're doing it in Anger in Ericsson.
Yeah.
So
in product, is that?
Yes, actually.
Nice.
Yes.
Yeah.
I'm not supposed to talk about these at the moment, but
potential product.
Yeah,
things
I mean, it's very nice. It's very nice.
Yeah?
It fits onto the ARM processors very nicely.
So
we run it on the quad-core ARM9 processor.
And you're using the concurrency there.
Absolutely.
Yeah.
In fact, we don't use one. I mean, we do this. What we talked about earlier. The products we make are run on ARM9s, and it's we actually use 2 languages. I mean, we use Erlang and C. So we use C for the stuff that has to be performant, and we use Erlang for the control stuff.
Yeah, that makes perfect sense.
And we mix the two.
Yeah.
What is the question of Erlang and speed? If you look at my laptop, I'm able to spawn off about 10 million processes, send a message to them, have them receive the message, and then terminate them in a few seconds.
Yes.
Why are people complaining about speed?
Well, the people who don't use Erlang are complaining about speed because they perceive it to be slow.
And that's a sequential code they're thinking of.
Yeah, I mean, if you do a compression algorithm or cryptography in Erlang, it will be slower. But if you do this handling multiple concurrency, it should be faster.
Well, that's our experience.
Yeah, I mean, that's why WhatsApp and people like that choose Erlang, because it's really that's where it excels. I mean, it was designed for telephone exchanges which have hundreds of thousands of simultaneous connections in them, and they're typically, a packet comes in, do something very quickly, then go to sleep for a potentially very long time, and then do it again. So there's no notion of storing state in a database when you're not doing something. Concurrency isn't sort of do something, put your state in a database, go to sleep. So you avoid all this mismatch of putting stuff in and out of a database.
It models. It fits with the world it's modelling. Yeah.
Okay. Well, okay. Thank you for listening, and we're ready now for the next masterclass.